Thank you, everyone. My name is Tan Jianing. I am very honored to be here to presentation. I am a doctoral student from Southeast University. I am currently doing some research on quantum algorithm. Today, I would like to share with you some of my research on multi-party entanglement in Shor's algorithm. My presentation includes these 4 parts. First, some background information about this research. Second, briefly introduces Shor's factoring algorithm and the entanglement measure we used in this study. Third, I analyze the occurrence of multi-party entanglement in the algorithm. And last, some conclusions we have got. Part 1, Introduction. Firstly, I would like to give you a bit of background. What is information? As its name implies, information is what informs. It is not only an abstract math notion. Information cannot be separated from physical carriers. It can be converted between different physical carriers. Information processing is physical and governed by the laws of physics. So in 1991, Royal Lowen said information is physical. Computation is a kind of information processing, so it is also physical. Because macroscopic particles dynamics described by quantum theory is more accurately than described by classical physics, quantum algorithm is studied from the perspective of quantum system evolution. So, quantum algorithm is more in accordance with the laws of physics. Different from the classical computer, quantum computer is built from a quantum circuit containing wires and elementary quantum gates to carry around and manipulate the quantum information. This is debatable. It is the first quantum computer made in 2011. Roadmap of multi-photon quantum computer made by Chinese Academy of Science in 2017. This is a quantum computer made by Google in 2018. It can manipulate 72 qubits. And this is QSystem 1 made by IBM. It is the first conventional quantum computer. It is made in 2019. Quantum computer can realize highly parallel computing by unitary transform quantum superposition stage. So quantum algorithm can solve some NP problem exponentially faster than classical algorithm. Here are 2 remarkable quantum algorithm types. First, Shor's factoring algorithm. It can ramp exponentially faster than the best-known classical algorithm for factoring. Second, quantum search algorithm. It can run quadratically faster than the best possible classical algorithm. Next, I want to talk a little bit about present study. Quantum algorithms attract much attention due to their high efficiency compared to their classical counterparts. However, the reason for such higher efficiency remains unclear. Entanglement is an attribute unique to quantum systems, so some studies have tried to find the role of entanglement in quantum algorithms. Most researchers believe that entanglement is necessary to realize quantum computer, such like these 2 papers. However, there has also been much debate on the role of entanglement in making quantum algorithms powerful. A previous study indicated that quantum parallelism is the only quantum mechanics tool required by quantum algorithms to overcome their classical counterparts, but the role of entanglement has not been elucidated yet. Now let me move on to Part 2, Preliminaries. Shor's algorithm or Shor's factoring algorithm can solve factorization problem in polynomial time. The quantum circuit is like this picture. Usually, register for phase estimation is called the first register. Register for agent stage is called the second register. The algorithm is performed in two stages. The circuit before the inverse quantum Fourier transform is called the first stage. This is the first stage. And then the second stage is to apply the inverse quantum Fourier transform on the first stage. Entanglement quantification is referred to as entanglement measure. Thus, multi-qubit states often have difficulty obtaining the entanglement value. Numerous entanglement measures have been defined for the different properties of the state. Here are some famous entanglement measures: concurrence, Gregorian entanglement measure, geometric entanglement measure, and the entanglement measure based on the coefficient matrix. The measure we use in this study is the last one. The rank of coefficient matrix is an inherent physical property, since it is invariant and SLCC. Compare with other entanglement measures. Entanglement measure based on coefficient matrix is easy to calculate and capable of dealing with quantum pure states with arbitrary dimensions and parties. This is the definition of coefficient matrix. And then the entanglement value of quantum states can be calculated by this formula. Now let me move on to part 3, multipartite entanglement in Shor's algorithm. This is the definition of the factoring problem. Shor's factoring algorithm is to solve this problem. We can obtain exact formula of amplitude of passage 1. Passage 1 is the quantum state is the mathematical expression of quantum state after the first stage of the Shor's algorithm. In the case when the order R is equal to 1, the mathematical expression of passage 1 is like this. We can classify all the bipartition of the n-qubit system by row bits. First, all of row bits are in the first register. Second, all of row bits are in the second register. And third, part of them in the first register, others in the second register. In the first case, when all of the row bits of the coefficient matrix are in the first register, the coefficient matrix can be written as this matrix. And in the second case, the coefficient matrix can be written as this matrix. Now, in the last case, the coefficient matrix can be written as this one. According to equality condition for Kersey-Quartz inequality, for these three cases, the bipartite entanglement are all zero. Global entanglement of an n-qubit state is the sum of the bipartite entanglement measures associated with all possible bipartition of the n-qubit system. So, when the order R is equal to 1, Shor's factoring algorithm generates no entanglement. If there is at least one bipartite entanglement is not zero, the global entanglement definition is not zero. The algorithm will generate entanglement. When we group by qubit in the first register, passage 1 can be written as this. Obvious. When order R is equal to 1, we have this equation. But in the case when R is not equal to 1, we will find this inequation. Then we will certainly find the coefficient matrix, elements of which satisfy this relationship. The bipartite entanglement based on this coefficient matrix is not zero. So, Shor's factoring algorithm will generate entanglement when R is not equal to 1. To understand it more clearly, we give an example. In the case when x is 2, n is 3, then we can get the order I is 2. When we set qubit number in the first register is 2, at this time we can get the mathematical expression of abscesses 1 is like this. Obviously, this group is the same as this group, and this group is same as this group. When we choose the second qubit is row bit, the corresponding coefficient matrix is like this matrix. In this coefficient matrix, this group is not equal to this group, and this group is not equal to this group. According to Cassey-Cross inequality, the corresponding bipartite entanglement is not zero. So, in this case, the global entanglement is not zero. Shor's factor algorithm will generate entanglement. Okay, now we are going to take a look at the last part, conclusion. We have got the following conclusions. Shor's algorithm will not generate entanglement in two cases. First, the input state of the second register is an explicit eigenstate. Second, the order I is equal to 1. Compare with published results. A published study demonstrates that there is entanglement of an unbounded number of particles in Shor's algorithm, and it gives a simple case in which the state is blocked. It is easy to find, although the state can be written as the form of product state. But there is entanglement between qubit 0 and qubit 2, qubit 1 and qubit 3. We call it partial entanglement to differentiate from full entanglement. So, this study neglects partial entanglement. A published study gives a conclusion that for some values of n and choices of x, Shor's algorithm produces no entanglement. There is a simple counterexample that when x is 2, n is 3, I is 2. When we set qubit number is 3, the corresponding periodic state is like this. Obviously, it is an entangled state. We suspect that this is because the entanglement measure the paper used is a Grovian entanglement measure. The paper gives an algorithm for obtaining Grovian entanglement measure, but it easily runs into the local optimization solution. Besides, the quantum states paper focused the states in the first register. After the measurement, the state we studied is all the states, including states in the first register and also states in the second register. In the first stage, the algorithm acts on all the states, and before measurement, all the states may entangle together. This study neglects it. There is an interesting question. Does it mean entanglement is relevant to achieve quantum algorithm speedup? In the present case, we can only demonstrate that in practical works, Shor's algorithm will always generate entanglement. When designing new quantum algorithms, using entangled states might be considered as a basic rule. To provide compelling evidence in the future, we need to develop new useful quantum algorithms, completely depend on entanglement for quantum speedup. Thank you. If you have any question, you can contact me with this mailbox.